And we are live. So welcome back to what is not officially the second of a two-part lab, but this week's lab and last week's lab have a lot in common. You're referring to the same chapter in the Johnson book linked on Canvas as last week, and it's useful to have any notes that you might have taken from last week on hand, because last week we learned what a sediment was and what substances can constitute a sediment. And this week, we learn more directly about the properties of the rocks that form from these sediments, which are unsurprisingly known as sedimentary rocks. So we can have sediments that are made, or anything that settles. Those particles, those things that settle can be rock fragments, known as clastic sediments, or they can be chemical sediments that form from chemicals that are dissolved in water. And likewise, we have different types of sedimentary rocks. We have clastic sedimentary rocks made of rock fragments, and chemical sedimentary rocks made of precipitated chemicals. And sometimes those chemical sedimentary rocks will actually get another label. If they were actually precipitated by a living organism, they will be known as a biogenic sedimentary rock. And a good example of that is when shells form. And one reason that's important actually is because sometimes chemicals just precipitate on their own, like if the water evaporates, but often it takes energy to synthesize calcium carbonate from water, and the organisms actually provide that energy that lets calcium carbonate form. And calcium carbonate is actually what mineral that you folks have seen a couple times before. I'll give you a hint. The calcium, it sounds a lot like calcium.
Calcite?
Calcite, yes, absolutely. Calcite, which is a mineral you saw before, is a major mineral in one of the chemical or sometimes biogenic sedimentary rocks we see, aka limestone. And so you all did an in-class evaluation pretty recently. There's an online survey that some of you have taken. That's still open, by the way, in case any of you want to provide course feedback or anything of the like. I believe I'm nearly positive it's open until Friday. I've been getting a lot of emails from IT that don't completely make sense to me because I'm not sure how everything works here still, but the impression I got was that there were some issues with the surveys on Canvas and that those have been fixed now. So this lab will be due Monday, April 5th, which is next Monday, and that's the only thing due next Monday. I mistakenly emailed you all to say that there was also a quiz due that day, and then I realized that doesn't make sense. I have the quizzes be due the week after the corresponding lab has been finished. So there's going to be a quiz on labs 6 and 7 due on April 12th, but for next week, you just have to do this lab. And I also wanted to mention that a feature that I haven't really been emphasizing much, but that I'm working to be more on top of now is Dr. Bird set up discussion sections when she taught this class before. And there's a discussion board on Canvas for labs 6 and 7 that you are welcome to use if that's easier for you than email, if you have questions, if you're working on this later, or if you just have sort of general interest questions about sediments or sedimentary rocks. And I'm doing my best to keep those updated, and I will see the responses and check those. So if you post anything there, as long as it's not right before the due date, I'll have a chance to look at that. And that's there's a link to the discussion section. There's a link to the discussion board at the top of the intro text for this lab if you want to use it. So any questions? Okay, so let's learn about sedimentary rocks a little bit. Let me just make sure that, okay, nothing in chat. So let's start with clastic sedimentary rocks. And clastic sediments are rock fragments. Clast means rock fragment, whether it's a big rock fragment like a boulder or a tiny one like a little piece of mud. And it's kind of hard to sometimes think of mud as being made of individual particles because you take a scoopful of mud and it's just goopy, yucky stuff, but it's actually made of tons and tons of tiny, tiny particles. Just they've been ground down a lot. But the clastic sediments are rock fragments, like the sand on this beach in Oregon or the pebbles on this beach in Oregon. And those clasts are breaking off of rocks. And they're breaking off of different rocks. At this beach in Oregon, actually, you have some basalts, which are a volcanic rock, an igneous rock that erupts at the surface, or an extrusive igneous rock that came from volcanoes. Actually, in this case, really far away. So if you go to the Oregon coast, you find lava flows that are actually from hundreds of miles away from the Columbia River basalts, which are a gigantic lava flow that covers a lot of the state. But anyhow, you also have rocks from further inland breaking down and being carried to these beaches by rivers. And so clasts can be from any type of rock. And one thing we look at when we study clastic sedimentary rocks is actually we look at the minerals that are making up the pieces to see what's in them, whether they're dominated by quartz or whether they're dominated by plagioclase feldspar or alkali feldspar, or whether they still have a lot of rock fragments that have mafic minerals in them. And it can tell us a couple different things. It can give us a sense of how far the sediments have traveled, and it can also give us a sense of what rocks the sediments originally came from. So we have a number of methods of classifying clasts. And the first thing we often look at is the size, whether we're dealing with boulders or smaller pebbles and gravel, or sand or silt and clay. And this is often especially diagnostic because it relates to the speed of the water that carries the clasts. Sediments can be carried by wind and glaciers, but a lot of the time the mover of sediment is water. And the size of the clasts actually usually tells us what the speed of the water that was carrying that sediment was. The sorting tells us whether the clasts in a sediment pile or in a sedimentary rock are all the same size or if they're all different sizes. Poorly sorted rocks are going to have a mix of grain sizes, so you're going to have some pebbles mixed in with mud and sand, whereas a well-sorted sedimentary rock is going to be made of clasts that are almost all the same size. Angularity tells us whether the clasts are rounded, which indicates that they've been transported for longer, meaning the water's had more time to round them down. And if they're angular, that indicates that they haven't actually traveled very far. Now, I mentioned mineral composition, and for clastic sedimentary rocks, mineral composition is a bit less important than it is for, say, igneous rocks. And that's because clastic sedimentary rocks are first and foremost named according to clast size. And one thing to consider is that you can have pebbles that are originating from different rocks. You can have black pebbles that come from basalt, and then gray pebbles that come from granite, and then sort of pink pebbles that come from a sandstone with a lot of feldspar in it. And the same thing with mud. I'll show you some pictures of how you can have different colored mud that have different mineral compositions. So we don't So the first thing we jump to with clastic sedimentary rocks is not mineral composition. However, we still want to study where the sediments came from, and we want to study what minerals are making up the clasts to get a sense of that. And it also tells us how far the sediments have been transported, because some minerals are slower to break down than others. Remember that quartz basically doesn't chemically weather, at least not heavily. So a sediment that has been transported a long way and had the water both physically and chemically breaking down the sediment is going to have a lot of quartz and not as much feldspar and very little in the way of mafic minerals, because the mafic minerals break down much more easily. And all of these tie into an overall concept that this lab doesn't really emphasize, but I did want to mention, and that's sediment maturity. And a mature sediment has been transported a long way. The idea is that with human emotional maturity, that people have had a long time to develop appropriate responses and get a sense of how to go out through the world. And sort of likewise, sediments that are mature have been in the system for a long time. They've been transported a long way. So if a sediment is mature, it will usually have smaller particles because the larger pieces have broken down. It will be pretty well sorted because there's been time to settle and differentiate. It'll be more round because the water's rounded it more, and it'll have a lot more quartz and not as much feldspar and rock fragments. So any questions so far? I'm going to go over all of these briefly in detail. Okay then, so for class size, again, for a clastic sedimentary rock, one made of rock fragments, the clast size is going to be what gives the name to the rock. So conglomerate, for example, which is this rock on the upper right, is made of lithified pebbles or gravel, aka pieces of rock that are larger than sand, basically. And if you look at the conglomerate, you'll see that there's a cement between the large pieces. And conglomerates tend to be very poorly sorted and have a lot of mud-sized and sand-sized particles also. But they're defined by the presence of the pebbles. The clastic sedimentary rocks are going to be defined by what the largest particles are. Not counting outliers, like sometimes you'll have something called a sandstone that has maybe maybe like you'd have like one small pebble in the area shown in this picture. But in this case, you can see that there's a lot of pebbles. It's not just like there's one, it's mostly made of pebbles, and then there's mud and sand kind of gluing it together. So sandstones are made of sand-sized particles almost entirely. Sometimes they'll also have silt and mud tying them together. Sometimes you go to a beach and there's a lot of mud there also, whereas sometimes you go to the beach and it's more just sand. So sandstones are usually better sorted than conglomerates, but not always. And silt and the even smaller clay make up rocks known as siltstone and shale, which can be pretty hard to tell apart. We're not going to worry about that distinction too much for this class. But in general, siltstones and shale are sedimentary rocks where you can't see or feel the individual grains, because I know that probably all of us as a kid played with mud at some point, and mud feels smooth. You can't really feel individual particles. If you were doing this lab in person, an easy way to tell apart a sandstone and a shale is to feel them. A sandstone is going to be kind of coarse, like sandpaper, because the sand-sized particles are larger. And yes, like grit, precisely. And grit is kind of similar to sediment size in that you have different sizes of grit that you're using to. But yeah, different sizes of grit. It's kind of a way to think of sediment also. Very good point, Heather. Now, some sediment, remember, is carried by wind or ice, but the vast majority is transported by liquid water, and the speed of the water matters a lot. Faster water has more energy, and if something has more energy, if you have more energy, you're going to be able to carry a lot more than if you're really drained and your muscles are tired. Then you're going to have a friend to it. Likewise, if water is moving fast, it has a lot of energy, and it has the power to move around and carry pebbles and even boulders in some cases, if the water is moving at the speeds that you find in flash floods. So in the stream on the lower right, you can see pebbles and boulders, and that's because this stream is moving fast on its own in this picture, and also these mountain streams where the rivers are first forming high up in the mountains also periodically experience flooding, like when the snow melts, for example, and those floods have the energy to carry large boulders. In contrast, in the upper right, we have a river that's meeting the ocean at a delta, and in places like the California Delta, where the two rivers in the Central Valley come together, or the Mississippi Delta River Delta around New Orleans. The river has slowed down quite a bit. By that point, it's usually flowing very gently horizontally, and the water doesn't have a lot of energy. By that point, most of the large clasts, the pebbles and the boulders, will have dropped out. There'll be some sand and then just a lot of mud left over. And just like the Bluesman muddy waters, the rivers that are reaching their deltas tend to be really muddy. They have a lot of suspended silt and mud in them. And so one thing to consider with flooding is that the danger of a flash flood is that you or your property, like your car, could be carried along by fast-moving water, just like a large clast. And unless you're like in that one, if you've seen the older episodes of the Magic School Bus, there's an episode where the teacher, Miss Frizzle, puts her class in like these rock suits and has them experience what it's like to be sediment, and they don't get hurt because they're in rock suits. But you don't want to have the experience of being a piece of clastic sediment. You don't want to get carried by a flash flood. And flash floods often happen in desert areas where there's not a lot of rainfall most of the year, but then when it does rain, the soil doesn't absorb the water very quickly, and there's not a lot of plants, and you just get the water going in this torrent down the slopes and carrying everything in its path, breaking off large pieces of rock and carrying those large pieces of rock. This Santa Barbara isn't as much of a desert as the Antelope Valley or Death Valley, for example, but it's still a pretty dry area that's prone to flash flooding. And I was in the area when the Thomas Fire happened, and in the subsequent months, there was some horrible flooding that carried boulders this large down to people's houses. And so you just want to take care of this. That's one reason why you always want to take care of paying attention to the weather if you're in a desert area, especially because if it's going to rain, especially if it's going to rain for like the first time in months, you could have a flash flood. So setting that sort of morbid example aside, here's a chart that shows you approximately what types of rock you form from clastic sediments of different sizes. And notice again that you can't really see the individual grains in the silt or the clay or the respective siltstone and shale that form from them. And don't worry too much about the difference between shale and mudstone. It's a distinction as to how heavily layered they are or not, but that's not really something we have to worry about much for this class. So any questions about clast size or about how water speed relates to clast size? Because that's something that comes up in this lab. The fastest water will move pebbles, slightly less water that's kind of like still has ripples. Water that's about the speed of waves will move sand. That's why beaches are sandy, because waves have the energy to move sand, but not really pebbles as much a lot of the time, depending on how stormy it is. And then really slow moving rivers can only really carry mud. Now, one reason I mentioned sorting having to do with maturity, kind of the overall concept of how long sediment has been in the system, is that if sediment has been transported by water longer, there's going to be more of a chance for particles of different size to separate. If you take a bunch of sediment and put it in a jar like this, it'll be jumbled up at first, and then over time, the larger pieces will start to settle out, and then the sand-sized particles will start to settle out, and finally you'll just be left with water that has a bunch of suspended clay and mud in it. And so one thing we actually see is that finer-grained rocks tend to be better sorted. The coarse-grained rocks, like conglomerates, have a mix of large particles and small particles, and they're defined by the presence of large particles. Because if you think about it, the fast-moving water doesn't really make a distinction between small particles and large particles. It kind of carries everything. But when the water slows down, the large particles that are left over kind of fall out, and the water only has the energy to carry sand and mud. When the water slows down even more, it's going to lose the energy to carry the sand, and it's going to drop the sand out and just be carrying mud. And again, sorting and class size aren't exactly the same, but they go hand in hand. In general, smaller grained clastic rocks are going to be better sorted. Now, Angularity talks about whether the pieces making up a sedimentary rock are all sharp and jagged, like in this breccia, or whether they're more rounded, like in this conglomerate. So actually, there are a few cases where clastic sedimentary rocks are named differently, even though they have the same approximate clast size overall. A conglomerate and a breccia both have pebble or gravel-sized rocks or clasts in them. But the difference is that the pieces in a conglomerate are rounded, whereas those in a breccia are more angular. I kind of like this picture because this piece looks like Hawaii, and this piece looks like a pentagon, and you've got all these geometric shapes, whereas these all look kind of rounded. Does anybody have a guess as to what kind of place we could find a breccia? What kind of place would cause rocks to be broken up? And then the pieces from those rocks won't travel very far. What's a place where that could happen? I'll give you a hint that breccias often form in areas where water doesn't really carry it far. Indeed, actually, you find breccias often at the base of a mountain, like in an alluvial fan, where the clasts don't get carried very far. Remember, alluvial fans often form in deserts where there's enough water present to carry the sediment to the base of the mountain, but then there's not a very constant water flow that actually then carries the sediment to the ocean. So breccias form there. One other place they form actually is faults. There's a specific type of breccia known as a fault breccia, and that's actually a feature that we find in the fault zone of, say, the San Andreas Fault. Because when earthquakes occur, the Earth is moving, and the the rock on one side of a fault boundary and the rock on the other side of the fault boundary are energy builds up, and when they move, there's usually going to be some breakage that occurs. Since the rocks are jammed up next to each other, when energy builds up and then gets released with the rocks moving, the rocks get broken up into tiny pieces. Now, the San Andreas Fault cuts through some pretty dry areas of California. A lot of it is in the middle of the desert. And so without a lot of rainfall, the broken up fragments of rock broken by that fault don't get transported very far. And you'll often find, sometimes we can get evidence of past faults existing by the presence of fault breccias if we map where they're located. And we find lots of jagged, broken up pieces of rock in the area around the San Andreas Fault, especially in the desert areas, because the water doesn't transport it very far. So any questions about angularity? In summary, the farther that clasts get transported, the more rounded they get. Okay, cool. So as for mineral composition, to simplify, we often break the ingredients. We often group the ingredients into three categories. We look at rock fragments, so pieces of rock that are so clasts that are made of pieces of rock that aren't individual minerals, that are like broken down pieces of basalt or granite. We look for feldspar crystals, and we look for quartz crystals. And this is something we can often see easily with sandstone, because with sandstone, the clasts are still large enough for us to look at. There's actually several types of sandstone that are all known as sandstone because they all are primarily made of sand-sized particles, but they're given an additional classification because they have slightly different mineral compositions. So, for example, there's Arcose sandstone that has quartz, but also has a lot of feldspar in it also. It has about, if you are to actually look at the individual grains in here, something like 1 in 3, or at least more than 1 in 4, will be consisting of plagioclase feldspar or orthoclase feldspar. And again, what mineral does the pink color in this one come from? What's the pink feldspar you've been looking at in past labs? Good guess. Good guess. You have to be careful sometimes with telling whether you're looking at rust staining or whether you're looking at pieces of orthoclase feldspar. Orthoclase feldspar is the pink feldspar that you've looked at in the past couple of labs. There's also something known as a lithic sandstone that has quartz feldspar, and then about 1 in 20 grains will be fragments of pre-existing rocks. And that's an important distinction because these pre-existing rocks are rocks that still have mafic minerals in them. Lithic sandstones tend to be the least mature sandstones because they still have pieces that are possible to identify as belonging to rocks, like, oh, this is a piece of granite, or this is a piece of basalt, or this is a piece of gabbro. And those tend to break down pretty quickly. The rock fragments tend to break down into quartz and feldspar, and then the waste made from the mafic minerals breaking down pretty quickly. So if you have a sandstone that has any rock fragments in it, it's going to be a lithic sandstone, and it's not going to be very mature. It consists of sand that hasn't been transported very far. And lithic sandstones will often be darker. And the most pure sandstone is quartz sandstone. And quartz, remember, essentially doesn't chemically weather. Quartz is very hard to break down. It just breaks into tinier and tinier pieces. And even then, quartz actually doesn't tend to weather. Quartz is hard to weather to a smaller amount than sand. But quartz sandstone is going to be almost pure quartz, and it's the most mature sandstone. It's the sandstone that's made of particles that have been in the system longest. Now, another example where you can see different colors reflecting different mineralogies is sometimes you can see different colors of mud. If you go to Iceland and visit the Blue Lagoon, people are convinced that the mud on the base of the Blue Lagoon is good for your skin. I'm not really sure if that's true or not, but the mud at the Blue Lagoon is a different color from the mud on this gentleman who's getting a mud bath at the Dead Sea. And they're both mud. They're both mud, and that mud could hypothetically be lithified into mudstone, but they have different minerals in them. There's different minerals dominating them. So you have to consider mineralogy because it does tell you where the sediments are coming from originally, even though the predominant name for the rock that forms is still going to be named according to size. So if the mud on this lady's face were to turn into rock, it would be a mudstone. If the mud on this gentleman were to lithify, it would also be a mudstone. They would just be mudstones with different mineralogies. Does that make sense?
Yeah.
Cool. And it's something you can really see easily with conglomerates, actually, because conglomerates, it's very easy to see the rock fragments still. And you can see that some are going to be full of mafic and volcanic rocks. Some are going to have a lot of pieces of other sedimentary rocks. Some are going to have bits of metamorphic rocks, which are the one type we haven't really gone over yet. And again, these are both conglomerates because they both are made of largely rounded, large pieces of rock, but they're made of different types of rock fragments, because if you have a river cutting through a mostly volcanic mountain and breaking rocks off of that, it's going to produce different looking clasts than a river that's cutting through a mountain that's mostly made of sandstone and mudstone. Like in Santa Barbara, we don't have a lot of volcanic rocks, so we do have some conglomerates that are formed from the erosion of the mountains, and it's mostly made of like sandstone boulders it's mostly made of clasts that are coming from other sandstones. It's a little bit confusing, but remember that sedimentary rocks can break into pieces and then become part of other sedimentary rocks. Any rock can break down into clasts and become part of a clastic sedimentary rock. And again, that ties into the overall concept of sediment maturity. The least mature sediments are those being deposited, if we're talking about water, in cases where you have fast-moving water pretty early in the river system, if you're considering how a river starts in mountains and will flow to the ocean, to sea level, the most mature sediments are often those deposited where the rivers meet the sea. And that's actually one reason why the sediment on, say, the Gulf Coast of the United States is such pure quartz sand, because it's been carried by really long flowing rivers like the Mississippi River that have had a long time to let the sediments get sorted, essentially. So in summary, you'll have fewer large clasts as the sediments get more mature. The angularity will decrease, the sorting will increase, and you'll have more quartz and less feldspar and fragments that contain mafic minerals. Now, something else I want to mention, and actually this, Heather, this is iron, actually. This is a case where you do find iron becoming important, because when clastic sediments actually get converted to sedimentary rocks, there's usually fluids flowing around the grains, and those fluids have dissolved ions in them. So this is actually another place where chemicals come into play. And yes, actually, I'm trying to think about how much I know about how bricks are made, but I think the red color in bricks comes from iron, from oxidized iron as well. But anyhow, so the water flowing around the sediments has dissolved ions in it, and that actually plays a role in helping the sediments be converted to sedimentary rocks, because minerals will precipitate in between the pieces and help glue them together. The pieces of rock will just be sitting around, and the water flowing around it will deposit minerals like hematite, rust, the iron that you're seeing showing up here, or calcite, calcium carbonate, aka the mineral that dissolves in acid, or in some cases silica. There's a little bit of silica dissolved in water. It doesn't dissolve very well, but one consequence of that actually is that since it doesn't dissolve well, it's pretty willing to precipitate, and so often you actually get sedimentary rocks that are cemented together by silica that's come out of the water. And this is part of the process of diagenesis, which is a blanket term for the series of processes that convert sediment into sedimentary rocks. And in this lab, you'll be looking at a couple different types of cement. You'll be looking at some rocks, some conglomerates to get a sense of what is cementing them together. And you can figure that out by looking at the color of the cement, because sometimes, like, the distinct rust red color tells you it's hematite, or if it fizzes, that tells you it's calcite. So any questions about clastic sedimentary rocks before I move on? And you can kind of see how this is actually a quartz sandstone that's been cemented together, and you can see there's this stuff is new silica that grew in between the sand particles. And that's one difference between a sedimentary rock and just unconsolidated sediment. There's actually a new mineral that's grown in between the grains to hold them together. And it's very much just like cement in construction as well. This is kind of like bricks being held together by cement in a way. So chemical sedimentary rocks are those that form not at all from pieces of rock, but solely from chemicals that were dissolved in the water. So that can either be inorganic, like you can have water evaporating and leaving behind rock salt or rock gypsum, or it can involve living organisms. It can involve phytoplankton or snails or corals putting in the energy to take, say, calcium and carbonate ions from the water and convert those into the solid substance calcium carbonate, which is the mineral we know as calcite. So limestone is one of the most common ones, and these are all limestone. They're all colored slightly differently because they have slightly different textures. And also, if you remember, calcite is naturally a clear, colorless mineral, but it can be stained different colors by impurities very easily. So you can get sometimes very pure white limestone, like the chalk that forms the White Cliffs of Dover. That's made of calcium carbonate or limestone, and that's one example of limestone that comes from phytoplankton. This is actually fossilized marine plants that precipitated limestone out of the water. Those plants died, leaving behind their shells. Those shells lithified into sediment, and then tectonic forces brought the sedimentary rocks over the water later. You also have limestone forming in caves, which is one example where living organisms are usually not as heavily involved. You have formations like stalactites and stalagmites form from water dripping and leaving behind little bits of calcium carbonate. Or you have places like Mono Lake where the water levels fluctuate a lot, and if the water drops, that will cause limestone, a specific variety of limestone known as tufa, actually to precipitate out of the water. So the key thing is that limestone is considered limestone. The key thing to remember about chemical sedimentary rocks versus clastic sedimentary rocks is that, as the title indicates, for chemical sedimentary rocks, the chemistry matters. The minerals matter a lot. Limestone is defined by being made almost entirely of calcite, whether it's formed from cave drippings, whether it's formed from evaporation, or whether it's formed from tiny organisms. And these are just a couple of the marine organisms that make shells made of calcium carbonate, precipitate them, and that when they die, leave those behind to form limestone. One reason I actually really love the way that, so phytoplankton are a drop of seawater has millions of organisms living in it. Microscopic single-celled algae, basically, that are actually very much the base of the food chain in the ocean. You have little creatures feeding on these and then larger fish feeding on those little creatures. And that's why you don't really have much in the way of large plants in the ocean. The food chain is based on these tiny organisms. They precipitate calcium carbonate and incorporate it into their cell walls. And when they die, since the calcium carbonate is a mineral, it doesn't instantly go away. It just settles to the bottom of the ocean and forms limestone. And you have larger animals, you have larger organisms doing this as well. The shells that the nautilus or snails or clams build are made of calcium carbonate, and the same is true of coral. The same is not true of our bones. We fish and the bones of vertebrates like me and my kitty who has run off are are actually made of a different mineral called apatite, which is a calcium phosphate. But it's still a really good example of how you do have some minerals that are precipitated by living organisms. And likewise, these are some of the limestones that form from these organisms. You get these phytoplankton forming these really nice chalky layers. And then also you'll have limestones that have visible fossils in them, which is really cool. You'll have what's known as fossiliferous limestone. And then, of course, limestone can precipitate on its own. It can precipitate in caves or in lakes like Mono Lake, where you get the specific variety known as tufa forming. But not all not all chemical sedimentary rocks are made of calcium carbonate, obviously. I mentioned that you do have some silica that gets dissolved in water. Since silica very much does not like being dissolved in water, as soon as the water level drops, basically it will precipitate out. And so there's a variety of quartz that is microcrystalline in that you have a very hard to detect, very fine-grained crystal structure, and that's called chert. And you often find that in ocean settings. And you can tell chert because it actually has the same conchoidal fracture that you observe in quartz. If you have a large enough piece of chert, if you break it, it won't experience cleavage. It will show this fracture pattern where you get these curved surfaces. And you often find it in lakes or in the deep ocean alongside mud, because the same because where you have the mud forming, where you have the mud lithifying into siltstone, you'll also have silica precipitating out of the water, and to some extent helping to cement the mud together, but also sometimes forming distinct layers that are just made of the microcrystalline quartz. And also chert can be formed by living organisms. There are some types of phytoplankton that, instead of building their shells with calcium carbonate, build their shells with chert, or basically a variety of quartz instead. And then we have rock salt. Rock salt is one example of a chemical sedimentary rock that forms without biologic input. It'll often form in deserts where you have water flowing into a basin, and then there's no outflow from that basin, like Death Valley, the lowest point in the Western Hemisphere, where you have water flowing into Badwater Basin, and then the water doesn't really have much of a way to flow out, and there's also so little rainfall that it just tends to dry up before it goes anywhere, and that leaves behind dissolved stuff, dissolved rock salt along with other stuff. And some of that other stuff can include gypsum. Gypsum, which you looked at in a past lab, is one mineral that often forms as an evaporite deposit as well, from calcium and sulfate dissolved in the water. Now, interestingly enough, coal is actually considered to be a chemical sedimentary rock, and it's considered to be a type of biogenic sedimentary rock because it actually forms as a result of living organisms. Coal is very rich in carbon because that carbon comes from decayed plants. Coal largely formed during a period of Earth's history that we'll learn a little bit about when we do the geologic time lab, and it's appropriately, actually, does anybody know what the period of geologic time is in which most coal formed? I'll give you a hint. The term carbon is important. That's something I'm not sure if you've gone over in lecture yet, or if that's something you cover in lecture, but it's actually a period of geologic time known as the Carboniferous period, because it was very early. It was the period in which life. It was not the first period in which life was colonizing the land, but it was the first time when you had large, widespread forests spread across the Earth, and the Earth's climate overall was very steamy. So you had these rich swamps full of plants just producing lots and lots of plant matter. And when those plants died, they would be buried rapidly under the weight of more plants. And instead of completely decaying, the hydrocarbons in the dead plants were buried and converted by pressure over time into coal. Coal is actually considered to be a sedimentary rock because it forms from dead plants accumulating over time. And you actually get a similar thing with oil and gas, because you often find oil and gas in shales, a type of clastic sedimentary rock that form from mud. But in places where you have a lot of dead plankton ending up inside of that mud, if you have it accumulating fast enough, the dead plankton will, through geologic processes, be converted into oil. And that's why fossil fuels are known as fossil fuels. They are literally from dead plants in the case of coal and dead phytoplankton in the case of oil and gas. And that's why you sometimes have shales that are considered to be organic shales, because because you have rock fragments mixed in with oil from these dead plankton. So any questions about chemical sedimentary rocks? So as for today's lab, the questions for today's lab relate to mineral content, determining whether a rock is either clastic or chemical, or whether you have any evidence of it being biogenic, and particle size. If you'd like more reference, you'll want to refer to Chapter 5 in the Johnson An Introduction to Geology book that's linked on campus, and that's the same chapter you looked at last week. Before you attempt the questions, in the Canvas exercise, there's a number of videos at the start. Make sure that you watch those and take notes on them, because that shows Dr. Bird doing a number of tests on the samples that you're looking at and answering questions about. Running tests like putting acid on them to indicate whether the clasts fizz, whether the rock fizzes, or whether the cement fizzes, which would tell you that you have calcite, because remember, calcite is the one mineral that really dramatically reacts with acid. And also using hardness tests, because one way to tell apart quartz from calcite is the Mohs hardness scale. Quartz is a lot harder than calcite, and also in some cases looking at color, looking at whether you see the red that is distinctly connected to the rust color of hematite, and then also looking at also looking at the particle size, because the videos sometimes let you see what's actually in the rocks a bit better than stills do. So as usual, I'll be around until 2:05 to answer questions. I'll be uploading this video later and uploading these slides in just a bit. And does anyone have questions before I close the recording out? And I have this pic I took in Monument Valley here, because this is a nice example of layers of sedimentary rocks. Mostly sandstone, but you see that there's some of this is just rubble, but there's also some conglomerates mixed in here that have larger sizes. Okay, so I'll turn the recording off, and then I'll be around to answer questions.